And welcome to Dog Talk. Yeah, that's Nani Note's tribute to the Car Talk Puzzler. And well, we're up here in Anchorage, Alaska. We're big fans of Tom and Ray. They introduced the merry-go-round puzzle. This was a few years ago, but we like this one a lot, and we use it in our high school geometry class. Now, the idea was to find the area of the floor of this merry-go-round. That's the area of the big circle. Take away the area on the inside because we're not going to paint that spindle. Presented itself with a bit of a challenge because, well, I can't get to the center. I can't measure a radius or a diameter of either of these circles. So we're going to simplify this and say, hey, well, what are we really after? Well, we do know that this shape is an annulus. That is, I'm going to take this one circle, and I'm going to take away the circle on the inside. And I could think of this as a pair of concentric circles and the area bounded in between them, but it does have a name. It's an annulus. And we got that measurement. We said that Krusty was able to put his tape measure right there. So that right up against that spindle on the inside and just all the way to the edges of that circle on the floor. One measurement. Don't care where you took it. And as I recall, that was 70 feet he came up with. So Krusty measured 70 feet with his tape measure. Was that good enough? Well, of course it was. And now let's do the math and we'll see how elegant this solution can be. So we got to clean this up just a little bit here. Let's take this away and let's pull out some theorems here. First off, I don't care about this 10-1. That's only according to our textbook. But really, in simple terms, a tangent, that is this yellow line, is perpendicular to the radius at the point of tangency. So this radius, the radius of the smaller circle, perpendicular to this tangent. That segment is, of course, a tangent chord. It's tangent to the wee circle, and it's a chord of the large circle. All right, so we got that much. And then we had another theorem that was really, really convenient for us, and that's our other theorem, that if a chord is perpendicular to a tangent. So now forget about the little circle, but I'm looking at this chord. It's perpendicular to this radius. I could draw the radius all the way through to this red circle. Not necessary. I draw it there. It's perpendicular. Then it bisects. So this piece is the same as this piece. We're really just about there. We've got this all figured out. So now let's get rid of those theorems because they're taking up too much space. We know that the area of the annulus, that's the area of this circle, minus the area of this circle. Again, easily done. If we knew those radii, we don't know them, we don't need them. Let's just substitute these equations. And we're going to say pi r squared. And we're going to use capital R for the big radius and the wee r for the smaller radius. Now, I think I forgot to draw something. Oh, yeah. Well, where's that triangle? We need the big radius. Oh, yeah. I'm going to draw the big radius right there. See, that's the radius of the larger circle. We'll use the capital R there. Now, I can see here that I've got the makings of a right triangle. Now, if I've got a right triangle, then I should have some other measurements here. Well, hang on. Let's just keep going here. I'm going to factor out this equation. Factor the pi out. That's a constant, as you all know. And you probably have seen the area of the annulus written this way. But now we can do some really clever arithmetic. And well, let's do this. Let's use the Pythagorean Theorem. And I'm going to refer to this side, this length of the right triangle, as b, the b leg. So remember, a squared plus b squared equals c squared. Or in our case, r squared plus b squared equals the big R squared. So we know that. That's Pythagorean Theorem. Let's rearrange the Pythagorean Theorem just this way. Solving for b squared. And just to this point, subtract r squared from both sides. That's, of course, the wee radius. And you can see now that I can take this equation, and let's make a substitution. Oh, yeah. Well, since r squared minus r squared is b squared, the whole equation simplifies to this, pi b squared. And since we did know that this measurement of b, well, it's half of 70. Again, going back to the whole bisect theorem, that's going to give us right there, 35. I perform my substitution, and there you go. So it's 35 squared times pi. And then I guess we could bust out a calculator. I mean, if you really need to see this. Okay, we'll bust out a calculator. There's 35 squared. So 1225 times, and there's our pi key. And there you go. Wow, that's a big number. Well, Krusty was right. You could get it done. And there you go. In decimal, rounded to the nearest square foot. And notice I wrote it the cool way here with the exponents. Now, there's one thing I want to illustrate here. I mean, we're done with the math, but I just want to drive this point home that as beautiful as this solution is, notice it really does not depend at all on the actual shape or the ratio between the two radii. Right here, I've got a constant. I've got a constant tangent chord. And as I change this, all of these, this annulus, all of these have exactly the same area. Now that's pretty cool stuff. So thank you again for watching Nani Notes, and I hope this has been helpful. It's helpful in geometry, and you can enjoy yourself watching a little car talk.